Good afternoon, everybody. This is Andrew Braham at the University of Arkansas, and today's Pavinar will be an overview of biobinders. And I'd like to thank the University of Guilin for recommending this topic. Just some of the logistics of the Pavinars. If you have a question anytime during the presentation, you can raise your electronic hand. So if you look up on the left side of the screen, just above the list of participants, there's a small hand icon, and if you click on that, it will identify that you have a question, and you can simply type the question into the chat box, which is on the bottom left-hand side of the screen, and I will be able to see that you have a question and record that, and then answer that question. Also, PDH hours, professional development hours, will be emailed to you after the presentation. So today's Pavinar topic will be an overview of biobinders, and biobinders are a component of biomasses which go through some sort of refining technique, and that refining techniques, just like traditional petroleum refineries, gives us many byproducts, including fuels, chemicals, fertilizers, and then also paving binders, and we'll be focusing on the paving binder side of things. So we'll start out with a brief background. What is biomass? What are some of the desirable characteristics? And then what are some considerations of using these biobinders? There's two types of, two large umbrella sources of biomass that we can use for biobinders, and that's either from crops and crop waste or from animal waste. Iowa State University has done an extensive amount of research in different types of crops and how their waste streams can be utilized in order to make a biobinder. And some of the crops that we'll focus on today include oakwood, switchgrass, and corn stover. And we'll look at some of the physical, chemical, and rheological testing characteristics of these materials. North Carolina A&T State University has done a lot of work with biomass from swine waste. So pig waste, the pig industry is big in North Carolina, and they obviously create a lot of manure from that, and how can we use that byproduct as a potential application in pavements. So they did some chemical and rheological testing along those lines. And then a couple years back ago at Transportation Research Board, the annual conference in Washington, D.C. in January, they had a special workshop on bio-based additives. And from that workshop, they put out a TRB circular EC165, which is a very nice job summarizing biobinders in general, and then going over 6 bio-based additives. So we'll quickly go over that circular. I'll provide some links too if you want to do a little bit more research, but there's a lot of good stuff out there that we can reference. So first of all, what is biomass? Biomass can come from crops, including algae, corn, soybean, palm oil, switchgrass, canola, all sorts of crops. I'm sure there's many more that can be added to that. And if any of you have driven through Iowa, you see a lot of corn, you see a lot of soybean, and that's one of the reasons why the Iowa State University has been very aggressive in exploring these biobinders, is because that's a big potential product from the state that can be provided. Then you also have other agricultural byproducts such as straw, sugarcane fiber, corn stover, and logging residue, and a lot of this is kind of the waste that is produced from agricultural processes. And a lot of times this waste is either landfilled or maybe used as a fertilizer or some sort of covering agent, but we're just trying to look for ways to create a little higher value out of what is traditionally considered a waste product. And then finally, animal waste is a big deal. I mentioned in North Carolina they have a lot of pig farms, so there's a lot of pig manure. And here in Arkansas, we actually, it's the corporate headquarters of Tyson, so we have a lot of chicken houses. Maybe there'll be future projects looking at chicken waste, because that is a huge concern on how to dispose of all these waste streams from large groupings of animals and what we can do about that. So these are just kind of some sources of biomass and what is it in general, so everyone's on the same page. Now, we could probably have a whole presentation on how biomass is processed. So we're going to kind of just stick with this one slide, but there's a lot more details out there in some of the reports that I'll reference later on that you can dig into. But in general, you have some sort of product, whether it be a plant product or an animal waste product. And you can see here, this is an example for palm trees. And if you look at a palm tree on the left there, that palm tree is about 10% oil and about 90% biomass. And the question we ask is, how can we extract that oil in an economic way in order to use that as a potential biobinder? So you can see through various processings, you have plantation residual, you have, and part of that you have oil palm fronds, you have the fresh fruit bunches, and also oil palm trunks. These are all residuals from the palm trees. You can further process those into what's called the mill residual, which has palm kernel cake, palm kernel shells, empty fruit bunches, and mesocarp fiber, all these different types of things, and pome, P-O-M-E. And from all these, again, through various processing techniques, you can extract some oil. And the oil products are crude palm kernel oil and just simply crude palm oil. So overall, there's about 10% in these, 10% oil in these trees, 90% biomass, and you can kind of think of it as a refinery. As petroleum goes in, you use pressure and time to extract the different fractions. The lighter fractions go up, the heavier fractions go down. And how can you create volume from these fractions as you process the palm trees? And generally, when we're looking at some sort of organic matter, a catalytic process is used to extract the fuels and the chemicals out of the palm tree in this example. And what are some of the desirable characteristics of bio-oils? Well, you want some sort of hydrocarbon structure, and that is, a hydrocarbon structure is a combination of hydrogen and carbon. And when you're thinking about biomass and biofuels, carboxylic acid molecules are very common. And here's a couple examples of carboxylic acid molecules. You have your carbon rings with the rotating double bonds. Those are the little hexagons. And you also have a carbon and a oxygen hydrogen pair sticking off of there, and it can be either with a double bonded oxygen or two single bonded oxygen. So just a couple different types of structures you can have there. And when you're thinking about bio-oils and you're thinking about traditional asphalt cement, there's a lot of hydrogen and carbon in traditional asphalt cement and also in these biofuels. So when you look at hydrogen, both biofuels or biomass and asphalt cement are approximately 8 to 11% hydrogen, and the carbons are in the mid-80s. So if you can find different materials with similar elements and molecular structures, then you can start asking the questions, can these materials, these biomasses or bio-wastes, can they actually be incorporated into asphalt cement? What's critical, though, is that you have good performance. So some of the performance characteristics is looking at the rheological properties. So rheological properties, this is the viscosity using the Brookfield rotational viscometer. It's the stiffness characteristics using the G-star sine delta measurements from the SuperPave DSR. BBR testing, that's creep testing for low temperature properties. Those type of things all fall under the umbrella of rheological properties. And also, if you're not using the SuperPave system, you can look at absolute or kinematic viscosity. You can look at penetration. All these different types of tests quantify the rheological characteristics of your material. The rheological characteristics, although critical, are nowhere near everything we need. We also need to make sure that these biomaterials are able to adhere to our aggregates. If there's no adhesion, then you don't have a bound material, and you basically have a very expensive gravel road. You also want to make sure that the material is able to coat the aggregate. If you're not able to get a very relatively thin but very comprehensive coating across the entire aggregate structure, if it just kind of clumps, and doesn't coat very nicely, you're probably not going to get strong long-term performance. You need it to be able to flow during construction. This is very important because as you're constructing a pavement, you want it to be workable under going through the screed, then going under those compactors behind the paving train, and you want to make sure you're able to get those air voids at the end of the day. And then finally, aging characteristics are critical, because if your pavement's not going to last a long period of time, then you're probably not utilizing your resources as well as you could. So you want to make sure that it's able to age well over time. Those are all the performance characteristics, but then there are also several other considerations. Leaching is always a concern. Whenever you're putting a new material into a pavement or pavement structure, you're always concerned about, as the rain falls down and the water moves through that paving material, does that leach any material out of the pavement, because then all of that water with leachate goes into the ground and into the groundwater table. You need to be careful of that. You also want to make sure that the biobinders are not water soluble. As it rains, you don't want them to begin to dilute and disperse and lose their good performance characteristics, as we defined on the previous slides. You want to minimize odor. No one appreciates bad odors, and sometimes when you're putting these materials into pavements, you're not sure exactly how the smells will affect the general public. Obviously, transportation and handling of the material is absolutely critical. If your asphalt plants are hundreds of miles from the source of this material, that won't be able to work out very well. And if it's not able to transport in a convenient form, you'll also have problems with that. When you get to the plant, there's always issues. Are you going to take these biobinders and blend them at the refinery? You'll need special tanks for those. Are you just going to simply fill up a truck and hope it blends as you drive down the road? Or is a plant going to designate a tank that's able to have a mixer to mix the biobinder in with the asphalt cement? So lots of different handling questions. And really, transportation and handling go a lot hand in hand with logistics, because if there's any sort of investment that either producers or contractors need to make, then that's certainly a consideration. And I know another big problem with using reused materials is a consistent supply of materials as well. If all of your harvest occurs in, say, September and October, and that's the only time you'll have this biobinder available, that could logistically be a problem if you're trying to plan for year-round operations. And then finally, the final other consideration, which is one of the most important, is economics, because you need to be very careful that you're not sacrificing performance and economics. If you're still able to meet specification and get good performance, you may be willing to pay a little more, but if you start spending too much money, you're going to expect to see a really large return on that investment. So economically, there's a lot of considerations in using these biomaterials. So that's just kind of a brief background of biobinders, just a little bit about what is the biomass, what are some desirable characteristics, and some general considerations of using. If anyone has a question now, if you could please raise your electronic hand and type the question in the chat box, we can address those at this point. Well, there don't seem to be any questions at this point, so we'll move on to talking about crops and how we can extract biomass and biobinders from crops. As I mentioned, there's been a lot of work done with this at Iowa State University, and I'm going to follow a very, very nice report that they put out, and you cannot click on that link on the screen that you see now, but I just placed the link into the chat box, and you can click on that chat box and open the report. It's a very comprehensive report, lots of good information in there, and so I'm going to kind of follow this report, a couple other sources I threw in there. But what they did is they looked at these non-petroleum based binders for use in flexible pavements. And they felt that there was a strong drive to develop and produce binders from alternative sources, and they felt that non-food source biorenewable resources are a good way to do that. And This is very interesting. There's arguments sometimes about whether or not ethanol is a appropriate material to put into gasoline, because that is taking food off tables. So what Iowa State was really trying to do is hone in on non-food source biorenewable resources. So they're not looking at any sort of diversion from a consumer's food stream. This is just what is left over after the food is produced, and how can we utilize that material. And they looked at oak wood, switchgrass, and corn stover, and they looked at physical, chemical, and rheological testing of this material. So for the physical testing, the first test they ran was the oil separation potential. And this is very important. If you're using a new material that's liquid based and it has strong separation properties, that could have significant effect on the performance. It could have significant effects on trying to blend the material successfully with asphalt cement, or if it's being used partially, or if it's fully being used as 100% biobinder, then there could be issues with coating. If you're having segregation in the tank and you start pumping out of the tank, then you're going to have a different material as you go through that tank. So the oil separation is critical, and they used ASTM D7173, and this is originally a test to look at the separation tendency of polymer from polymer modified asphalt. Very similar concerns. If you have a polymer modified asphalt and the polymer settles to the bottom of the tank, then you're going to be pulling out highly polymer modified binder at the very beginning, and as you go through that tank, you'll have lower and lower polymer levels. So it's very critical to have non-separated material. And the way they did this is that they stored a column of material for a time period, and then they extracted a sample from the top of the column, a sample from the bottom of the column, and they looked at the G-star sign delta. And they just wanted to make sure that you're getting similar G-sign delta out of the top and the bottom of that column. And they found that with proper blending susceptibility, separation decreases. So blending these biobinders, whether they are 100% biobinders or whether they're blended with another asphalt cement, how you blend that material together is critical. And there's a lot more details in the report, which you can find at that link. And then in a couple other topics we'll look at, they touch on this importance of blending. And there's certainly no universally accepted blending procedure for biobinders right now. I think that the technology is just in its infancy stage. And as we get more mature in this area, there probably will be more studies done on this. The point is, though, that it is important to blend it properly. Along with oil separations, the second test that they looked at were the specific gravities, and you can see that the specific gravities of the biobinders are quite a bit higher than traditional asphalt cement, about 0.2 to 0.3 tenths higher than the asphalt cement. And this is just a consideration during all stages of the process, from the mix design process. If you have a significantly different specific gravity, that's going to change your mix design pretty significantly. To the production of the material, if these biobinders are heavier, this means that they will sink if they're blended with asphalt cement. To the construction and logistics of construction, you want to make sure that you keep them blended properly, or else you probably do have susceptibility to segregation or separation. So biobinders are quite a bit heavier. So that was a little bit of the physical testing. For the chemical testing, they used two different devices, a GCMS, which is a gas chromatograph mass spectrometry machine, and also a Fourier transform infrared spectroscopy. And these are very nice pieces of equipment because they can look at very specific details of materials. And what I'm showing here is just a very high-level snapshot of what they can do. But if you go into the report, there's a lot of details about the chemical mapping of these oils and how that chemical mapping compares to asphalt cement. But in general, you can see here that the carbon, hydrogen, and oxygen contents of the corn stover, the oak wood, which is oak flower, and the switchgrass. And if you recall earlier, we saw the percentage of carbon and hydrogen in asphalt cement. Traditionally in asphalt cement there's about 8 to 11% hydrogen. So you can see in these three biobinder sources there's a little less hydrogen than traditional asphalt cement. And then in general carbon is 82 to 88% in asphalt cement. Whereas with the biobinders here, it's quite a bit less. It's down into the 40s and one up there at 60. So the chemical composition is slightly different between these biobinders and traditional asphalt cement. So that's something that kind of alerted them and they wanted to track during their research. They also looked at three different molecule types, and we're going to go over these a little more on the second page too. But you can see they have cellulose, hemicellulose, and lignin. And those are molecules that are not commonly found in asphalt cement, but they are made of these carbon and hydrogen and oxygen configurations, which are also found in asphalt cement. But let's dig a little deeper into the cellulose, the hemicellulose, and the lignin, just to see what's going on with those. So cellulose is kind of similar to asphaltenes. They have very high molecular weight, and they're long linear polymers. Hemicellulose has low molecular weight, and they're composed of polymerized monosaccharides. And then the lignin is an amorphous cross-linked resin, and there really is not any exact structure. So their take-homes from these three molecules are none of them are incompatible with asphalt cement. So these are found in some form or some very similar form to traditional asphalt cement. But they were cautioning, and they said it's very important when you're talking about how you treat the biobinder, and especially with their heat treatment and what they call their upgrading procedure. And these are very important because through proper heat treatment and through proper upgrading procedures, you will decrease the amount of water in the biobinder, and you will also decrease the amount of volatile contents. And you know, being around an asphalt plant, water's not very good and volatile contents aren't very good. So trying to minimize those two through the proper heat treatment and upgrading procedures are essential. So we went over the physical testing, a little bit of chemical testing, and then their rheological testing. They looked at viscosity over time. They also looked at the temperature and duration for developing biobinders. That goes back to the heat treatment, trying to produce these biobinders appropriately. They looked at short-term aging characteristics, and then they looked at low, high, and intermediate temperature performance grades. So how these materials perform in the PG system at low, high, and intermediate temperatures. And you can see here is a graph of G-star for the complex modulus versus reduced frequency, the master curves. For those of you familiar with the SHARP program, there were a dozen or slightly more than a dozen binders that were chosen for the SHARP program, the Strategic Highway Research Program in the mid-1990s, which developed the PG grading system, and they used these specific binders that had a wide range of properties. And they specifically chose them because they wanted to make sure that the SuperPave testing system was able to properly capture the properties of all of the asphalt cements that are used across the country. So if you ever are looking at asphalt cement and you see AAM, AAD, any sort of sequence of 3 letters with a lot of A's in it, chances are you're looking at one of those original SuperPave binder asphalt cement samples. Because when they went through all this testing and developing of the equipment, they also pulled out a large amount of samples from this set of material, and they've just been storing it. So whenever any new material comes out or whenever some new technique comes out, they can actually compare it to the original binder. So that's what the AAM and the AAD are, kind of traditional asphalt cement types, and you can see that these different blends of biobinders, it's just an example of 3 shown here, have quite different characteristics along those master curves, especially at the lower frequencies. Some of those biobinders have significantly lower stiffnesses, and then on the other end of the spectrum, they start getting a little more stiff at the higher frequencies. So just kind of a pictorial representation that we're not dealing with the same material. It's not a one-for-one replacement, and understanding how it's different is important to usage. So their conclusions at Iowa State is that when you're thinking about the temperature ranges you can use, it's about 30 to 40 degrees Celsius lower than asphalt cement. When you think about the unmodified biobinders, so 100% biobinder, 0% asphalt cement, they felt that the rheological properties do vary significantly from the asphalt cement. So we're not comparing apples to apples here. This is a different material and we need to proceed with caution. They also played around a little bit with adding polymer modifiers to the biobinders. So they're taking these 100% biobinders and then adding polymer modifiers, and that significantly changed the rheological properties, and in some cases it actually improved them. So I think that using 100% unmodified biobinders may not be realistic at this point, but perhaps blending it with some other materials can help increase the potential for them. And their overall conclusion were no significant barriers appeared. As all good researchers do, they recommended that more future work with different biosources be pursued. They also recommended that they look at more asphalt cement types and more polymer types to see if there's some sort of blending that could go on. And then you'll notice that all of the data that was collected was just for asphalt cement or the biobinder itself, and none of it covered the asphalt concrete mixture testing. So trying to understand how it reacted with the aggregate is also critical for moving forward. So that was just a very brief overview of the biomass from crops. Now we're going to look at some biomass from waste, but if there are any questions, please raise your hand and I'd be happy to answer them. Well, there don't seem to be any questions, so we'll move on to the biomass from waste. So this work has been done at North Carolina A&T State University, and they looked at the chemical and rheological testing of swine manure. Very similar basic thesis here, that there's an increase in demand for natural petroleum, and waste biorenewable resources could be used to supplement that. So again, we're not taking anything away from the food stream, we're just looking at current waste streams that may be used for other areas, but the use of biobinders could maybe be a better and more efficient use of this waste. And what they did is they used a hydrothermal process to convert swine manure to an asphalt binder alternative, and they tested some chemical and rheological characteristics of that. Unfortunately, I wasn't able to find anything online, like through the North Carolina DOT or anything, but if you're interested in finding out more about this topic, you can search for Dr. Elham Feeney, and she's at North Carolina A&T State University. And this presentation, well, the next couple slides were taken specifically from two articles. One was published November 2011 in the Journal of Materials and Civil Engineering, and the second was published in December 2012 in the International Journal of Pavement Engineering. And she was the lead author on both of those, and the titles have biomass or biobinder in them. So if you kind of just Google some sort of configuration of those things, they're pretty easy to track down what exactly it is. Now you would have to pay for those because they're not open source, but they are available if you're interested. So what is the hydrothermal process, and why is it important? So what we need to do is we have this swine manure, and we need to take out the stuff that we want, and we need to make sure that the stuff we don't want isn't still in there. So what it does is it utilizes the carbon that's in the swine manure, but it removes any nitrogen, phosphorus, potassium, or coliform bacteria. So the hydrothermal process is designed just to get that carbon and remove all those other undesirable materials. And there are three categories of hydrothermal processes, and they're pyrolysis, gasification, and liquefaction. And for pyrolysis, organic matter is degraded by a thermal reaction, and you have a char remain. So basically fire is pyrolysis, and you're left with a charred remain. And gasification is where the organic matter is converted to gas through thermal decomposition. So if anyone has oh wow, I just drew a complete blank. If anyone has a compost pile in their backyard, you'll notice that it smells, and that is a form of gasification, and that's because there's decomposition going on in your compost pile, and there is heat being generated, and those gases that are set off is from gasification. And then finally, liquefaction, which is the most useful for this research, is where you remove your hydrogen or the you use reactive hydrogen or carbon monoxide, and you're able to produce either liquid fuel, liquid oil, solid char, or some sort of asphalt type material from the organic matter. So by using this hydrogen and carbon monoxide, you go through this hydrothermal process, and one of the byproducts from that is an asphalt type material, and that's what was used for this research. And you can see here the chemical composition of the biobinder compared to AAD. So AAD is one of those sharp asphalt cements that we talked about earlier, and that is a very soft binder. So of the range of binders that they use, AAD was one of the softer ones. So it's one of the softer reference asphalt cements. And you can see here comparing the different components, the carbon, the hydrogen, the nitrogen, and the oxygen. The biobinder has slightly less carbon, about the same hydrogen, a little more nitrogen, and quite a bit more oxygen. So not a one-to-one comparison again, but you're kind of looking at similar ball players here. At least you're in the right ballpark. Now I could go off on a 10-minute rant about the different components of asphalt cement, which include saturated compounds, aromatic compounds, resins, and asphaltenes. But I think if you just all agree that these are the 4 molecules that are the building blocks of asphalt cement, we can go from there. So if you break down asphalt cement into different molecules, the vast majority of it is saturated, aromatic, resin, or asphaltene. Those are the SARA, S-A-R-A components. And you can look at, they have 3 different types here that they compare to. The biobinder is the first one. Then they also have an air-blown asphalt binder, which is the most brittle binder, and then the AAD binder, which is a very soft binder. So they kind of took the 2 extremes of asphalt cement, a very brittle, a very stiff, hard asphalt cement, and they took a very soft asphalt cement, and then they looked at the biobinder. So for the saturated compounds, you have quite a bit less saturated compounds versus either the air-blown or the AAD. You have significantly less aromatic compounds, just a fraction, almost only 2% of the content. You have almost double the resin, and you have double to quadruple the asphaltenes, or more than quadruple. So again, this is getting a little more out of the ballpark, but they at least have some components or building blocks. So what is kind of the take-home from these 2 tables? Well, the first one is that the carbon-hydrogen ratios are similar. So although they're not identical, the ratios are similar, and that was encouraging for the researchers. And they recognize that if you have a material that has a high asphaltene content or a high resin content, that means that you're going to have a very hard, a very stiff asphalt. And that's one of the reasons why the asphalt binder AAD was chosen, a very soft asphalt, because as they blended these 2 together, they were able to look at a harder material that's blended into the softer asphalt. So the first thing they did was viscosity testing. We're getting into the rheological testing now. You can see that they had a neat PG6422. That's the asphalt cement they used. Then they blended 2, 5, and 10% of the biobinder into the asphalt cement. So at Iowa State, they were using 100% biobinder, except when they added the polymers. Here, they're just blending a small amount into the biobinder. And you can see that as the temperature increases, the viscosity decreases. That's very expected. Another nice trend that you can see here is that the viscosity decreased in the same fashion as you increased the percentage of biobinder, so there are no nothing out of sorts there. And then as you got higher too, you can see that the influence of the biobinder changed a little bit. The numbers were a little closer. Overall, though, they found that the biobinder with the swine manure decreased the viscosity of the asphalt cement. Decreasing viscosity, that means that your material flows easier, and you would expect to see a decrease in stiffness, and that's what you saw here. So these are the master curves. You have the complex modulus versus your frequency. As these curves shift downward, the material is becoming less stiff. And you can see that the PG6422 is on top there, then the 2%, the red circles are below that. Below that is the 5%, which are the green lines, and then below that is the 10%, which is the purple squares. Now, something that jumped out at me right away is that it's very unusual to see curves that are entirely shifted as you go down. I don't know if you recall the work at Iowa State, but there the curves kind of swiveled around a point. So as you went to a frequency extreme, then the differences grew larger, but there was some point where they kind of overlapped. Here the curves are completely separated. So across their entire frequency range, which is across the entire performance of the pavement, in theory, that it will see, the biobinders were softer, and they decreased that stiffness. So pretty interesting trends there. The last test that they ran was the critical cracking temperature, and this comes from the bending beam rheometer. What we're looking at here is basically at what temperature will you start to see thermal cracking. When does it get so cold that just a drop in temperature will make the pavement, it essentially snaps and start those thermal cracks. And you can see the biobinder had a lower viscosity, it was softer, not as stiff, so you'd expect to see that cracking temperature decrease as well, and it did. So you can see as you continue to add more biobinder, the more biobinder you add, the more that temperature decreases. So some basic conclusions from the North Carolina A&T research is that a partial replacement asphalt cement can enhance the binder properties. That's their take on it. If you're looking at the price of material, you always have to kind of look out for these price comparisons, because you have to think about the transportation, the handling, any sort of plant or production modifications you need. But if you're looking at a material replacement cost comparison, this does reduce the cost of pavement construction. Biobinders are about a quarter of the cost of asphalt cement, and that includes all of the production. So a tank of biobinder coming out of the production facility is a quarter of the cost, 50 cents, compared to $2 a gallon of asphalt cement coming out of a refinery. Another large benefit from this is you're going to reduce some environmental pollution, and this can be from any sort of disposal site failures. So a lot of these large animal farms have retention ponds, which allow material to settle and dilute it and such things like that. Whenever you have a large collection of waste, however, there are problems potentially with the failure of any sort of containment mechanism you have, or of course the leaching down into the groundwater. So lots of potential environmental benefits as well, taking this waste material, keeping it out of landfills or out of retention ponds, and being able to use it in a different way. And overall, North Carolina A&T believes that this biobinder is a very promising alternative. So we had our background, we looked at some crops, we looked at waste biomass, and now we're going to go over that TRB circular about kind of a whole slew of different topics. But if anyone has any questions, I'm more than happy to take them at this point. Well, there don't seem to be any questions, so we'll move on to the TRB circular. So as I mentioned, this last and fourth section here is a summary of the TRB circular, and I will put the link into the chat box here. There is the link. You can download the PDF if you're interested. This came out in August 2002, so this is actually a session 2 years ago. So in January, 2012. In January 2012 at TRB in Washington, D.C., they had a special workshop that looked at these 6 alternative binders, had some very nice presentations talking about them, and they put together an electronic circular. And these electronic circulars are fantastic. They have electronic circulars for many different topics, but it's basically a state of the art of the state of the practice of some topic that's of interest to the paving community. There was an asphalt oxidation circular. There is a asphalt emulsion circular. No, there's a bunch of them. So this is one of those. And their hypothesis is that alternative binders can help save natural resources and reduce energy consumption. So you're seeing kind of these same themes. We're trying to reduce natural resources. We're trying to increase using waste products from other sources, and we're trying to reduce overall energy consumption. So the first material that was looked at, and you can see a nice picture of the mix over on the right, is they looked at microalgae, and they put it in at 0, 20, and 35% by weight of the binder. And what they did is they took the microalgae oil, blended it with the asphalt cement at those levels. And their conclusions, very broad, very preliminary work, was that the use of microalgae-based binders should be feasible, and they had similar rheological properties compared to traditional asphalt cement. So a very preliminary work, but very encouraging from the standpoint of microalgae. The second alternative binder reviewed was soybean oil, and they used 0, 1, and 3% of soybean oil by weight of the binder. Soybean oil, you may also see it referred to as soybean fatty acid, and they found out that the use of this is plausible. They found that it decreased the viscosity and decreased the stiffness of the asphalt binders, so that's very similar to what North Carolina A&T found with the swine manure. And they also found that the mixing and compacting temperatures were lowered. And this is a very nice finding because we're always trying to figure out ways to reduce energy consumption. We're trying to figure out ways to increase haul distances and keep that mix workable at the lower mixing and compacting temperatures. So this could be potentially a warm mix additive here if we are able to reduce those mixing and compacting temperatures while maintaining the proper performance we're expecting out of asphalt concrete. The third alternative binder that they examined was a rubber modified fractionated bio-oil. So this is actually work that came out of Iowa State as well. And we had mentioned briefly that they had used some polymer modifications, and one of those polymer modifications was using ground tire rubber. So they looked at anywhere from 85 to 90% bio-oil, and that should be 10 to 15% rubber. I don't think they had any blends that were 105% of mass. That would be a pretty interesting feat. But it's primarily bio-oil with a relatively smaller amount of rubber blended together. And they found that this performance was comparable to traditional asphalt cement. So before, when they were only using the bio-oil, this is a newer publication where they had fooled around a little more with these additives. Some of these additives are able to bring the biofuel or biobinders up to the performance of traditional asphalt cement. And they were also quick to point out that the tire rubber is blending with the bio-oil. So a potential concern is because you may be using slightly lower temperatures, or the temperatures of mixing may be different. You may not have the blending with the rubber and the bio-oil that you enjoy with the rubber and the traditional asphalt cement. But they were finding that they were able to blend the rubber in with the bio-oil. The next alternative binder is pretty interesting. It's an organo-nano clay, and specifically it's a montmorillonite. I'll say that quickly. And that's just a type of organic nano clay. And they basically put this in at 4% by weight of the binder and compared that to an unmodified. And now we're almost getting into more of a mastic, because a nano clay is a solid particle, unlike these oils or biobinders, which are more of a liquid. So they were exploring this specifically to look at aging resistance, because these nano clays have been known to enhance aging characteristics of other materials. And obviously when you look at deterioration mechanisms of asphalt concrete, aging is a significant driver of a lot of those deterioration mechanisms. So they were trying to use this nano clay to see if they could increase the aging characteristics of the material. And they found that they improved the short-term aging resistance, so kind of during the production and construction. In the first couple of years it didn't age as quickly, but then looking at longer term, especially when they started using the PAV, they did not see as many aging resistant benefits. So it may help a little more short-term, but long-term they didn't see as many benefits. So the final two binders that were looked at were, the first was waste cooking oil. Obviously we have a lot of restaurants that produce significant amounts of cooking oil. I've seen research trying to look at using this in automobiles, other applications, and this group tried to look at it in asphalt cement. And they looked at a neat asphalt cement, and then they looked at 30 and 60% of the weight of the binder. And they found that the oil reduced the PG of the base binder, so they were able to get a softer material, which increases resistance to thermal cracking, but it decreases the resistance to rutting. So if you shift both that high and low temperature grade downward, then you are running the risk of having a rutting prone mixture, but you are getting some thermal resistance. And they found that also there's a reduction in the fracture energy, which contradicts the increase of resistance to thermal cracking in a way. Fracture energy is another way to try and quantify cracking, so there may be a discontinuity there. And also a concept called fracture work. And what this means is that they felt it's more prone to fatigue failure. So thermal cracking is one type of cracking, fatigue failure is a second type of cracking, and they found that using this oil reduces the fatigue cracking. So those high numbers of cars going over the pavement, all those repetitions, you would have a chance of getting some fatigue cracking there. The final alternative binder that was investigated was using waste coffee grounds at 2, 4, and 8% of the weight of binder, and they compared that to unmodified. Kind of like the nano clay, coffee grounds are known to inhibit oxidation in other materials. So they were exploring if the use of these coffee grounds would either prevent or decrease the oxidation of the asphalt cement. And you can see here that they failed to prevent the oxidation. You saw a slight increase in viscosity and no significant change of the complex modulus. So you didn't really see a whole lot of performance enhancements, and it didn't really help with the oxidation, so not a whole lot of promising results here. But it's just interesting the different things that we can look at in the paving industry to try and see what are some of these materials that are traditionally either landfilled or disposed in other ways that we can incorporate them. Do they have high quality products that could enhance the performance of our materials? So in conclusion, the 4 alternative binders that showed a little bit of promise were the microalgae, the soybean oil, the rubber modified fractionated bio oil, and the waste cooking oil. The alternative binders that did not show as much progress was the nano clay and the waste coffee grounds. Now all of these results seem to be pretty preliminary, so early stages of research, and they did feel that there's quite a bit more that could be done to more robustly evaluate the materials, and so they all recommended that none of them were dead ends, and all of them warranted more exploration. So in summary, I will email you the PDH hours no later than Friday, February 7th. Within the next couple days, you'll be able to rewatch this Pavinar through the website. I'll have to get the link uploaded and such. If you have any topic suggestions, please do submit them either via the website or shoot me an email. I'm always looking for new topics and better topics. This spring is all set, but I've got nothing on slate for next fall. And then the next Pavinar will be Tuesday, March 4th, and we'll be looking at high levels of recycled asphalt pavement, or RAP, in asphalt concrete. So we went over a little bit of a background of biobinders. We talked about some biobinders that came from crop waste. We talked about some biobinders that came from animal waste. And then we also looked at a wide range of biobinders from the e-circular. But I'm now willing to take any questions. I see a couple hands that are up, so I will allow you guys to type your questions in the chat box. And I ended a little early. I apologize about that, but I'll be more than willing to stick around for people who have questions. So the first question is, are you aware of any publications that include an economic evaluation, such as a life cycle cost analysis, of traditional versus alternative binders? And I have personally not seen anything about that. However, if I would have to guess on a group that would do it, I would say it would be Chris Williams up at Iowa State. I'm actually Googling it right now to see if they have anything. And oh, here we go. There's a little article, and I apologize. Holy cow, there's a lot of stuff here. There seems to be an article on better roads that talk about it. Oh, nope, it's in the conclusion. So I just found a magazine article from Better Roads. It was produced a couple months ago, and they said that a life cycle cost analysis was something that they needed to do in the future. So to answer the question about a life cycle cost analysis, I really don't think there is anything out there right now, at least not that I found. And if someone finds something, please email it to me. I'd be more than happy to incorporate it. So the second question has any research been done on waste or algae in the oceans? And that's a great question. Obviously, there's a significant portion of the Earth is covered by the oceans. And I am not sure where the microalgae was from. I believe the microalgae was from a freshwater source. I think that they were looking at it from the option of potentially using something associated with a wastewater treatment plant, that microalgae. And so as far as I've read, I have not seen anything that has come out of work from the oceans. But I think that would definitely be something to explore, as there's a lot of resources in the oceans, and there's a lot of oceans. The second question is, do the percentages of carbon, hydrogen, oxygen, nitrogen, and other substances listed in biobinders come from gas chromatography? And I do not claim to be an expert on gas chromatography. Let's see here. But basically, yes, I think that gas chromatography is at least one way that you can take a material and analyze the different components within that. So I think looking at what elements you have within asphalt cement could be extracted from gas chromatography. The next question I have is there any test sections to evaluate the properties of these kinds of binders under environmental conditions? And this is an excellent question. All of the work that I talked about in this presentation was done in the laboratory. And that's a very important first step, but it is only a first step. And I'm not familiar with any of the, I cannot think off the top of my head of any test section that's put down. I'm pretty sure there's none at Min Road. I'm pretty sure there's none at NCAT. Now, I know that Dr. Feeney, she has worked with the University of Illinois, and I know the University of Illinois has an accelerated testing facility where you can put down pavement sections. So if I had to guess, one of the first universities that might put something out would be the University of Illinois, but I haven't seen any test sections put down to evaluate the material. The next question is, these materials, the biomaterials, have a natural tendency to degrade in time. And can I comment on that aspect? I think that's a good question. And I think that's one of the reasons why some of the researchers were looking to have these anti-oxidative effects on the asphalt cement, because at the end of the day, one of the biggest problems with asphalt cement is that it oxidizes and it becomes stiff. And are there ways that we can either mitigate or even prevent that from happening? Obviously, if you have a biobinder that starts degrading, then some of those beneficial tendencies won't come out. And I think we saw a little bit about that with the nanoclay and the waste coffee grounds. Those are supposed to help prevent oxidation, but because they did not do that, one could say that they degraded a little bit over time. As far as the other, like the bio-oils and those type of biofuels, I think that's why people were interested in looking at RTFO and PAVH materials, because they wanted to see how they would degrade under that time, heat, and pressure. And because there weren't any strong indications of the material degrading beyond what you typically see with asphalt cement, it's my opinion that we're not seeing a whole lot of degradation of the biobinders because they're biobinders. I think all materials degrade over time, and we're seeing some of that, but I don't think there's anything specifically with the biobinders that we need to be concerned with. Well, I think that's it. So thank you all very much for joining the Pavinar, and I hope to see you again next week. If you have lingering questions, feel free to stick around, but we're almost at 1. So if not, I'll let you guys go. Thank you very much and have a wonderful day.